Hello, welcome to our paper, Abstraction-based Incremental Inductive Coverability for Petri Nets. We present a novel approach to check the coverability problem of Petri Nets by combining IC3 with place merge abstraction. We named our method IC3 plus PMA. The outline of my talk is as follows. First, I will state the preliminaries of this paper. After that, I will recall some main ideas of IC3 for Petri Nets, which is the core of IC3 plus PMA. Then, I will state some definitions and principles of place merge abstraction and how to refine a coarse abstraction. After that, I will explain our algorithm, IC3 plus PMA. Finally, I will present our experiment results and future work. The first part, preliminaries. We consider classic Petri nets. P is a finite set of places, T is a finite set of transitions, and W is an arc function describing the relationship between places and transitions. M0 is the initial marking, with a number of MP tokens for each place P. There is a partial order over vectors of Petri nets. M1 is less than or equals M2, if and only if for each place P, M1P is less than or equals M2P. We define that prim M represents the set of predecessors of marking M in one step. Reach I contains all reachable markings from the initial marking with I steps. Reach contains all reachable markings from the initial markings. The coverability problem is to proving whether there exists a reachable marking, MR, from initial marking such that the target marking MT is less than or equals MR. If such a marking exists, then we can say the target marking is coverable, otherwise uncoverable. According to the definition of coverable, here is the definition of a coverable site. The coverable site of Petri net within I steps is cover I, which is the downward closure of reach I. The whole coverable site is the downward closure of the site of all reachable markings. There are many state-of-the-art methods to solve that question. IC3 is one of them. There exists an efficient implementation of IC3 to check the coverability problem of Petri nets without using SMT solvers. Now, I will simply state some main ideas of it. IC3 maintains a sequence F0, F1, and Fk, where Fi is a downward closed site called frame that over-approximates the coverable site within S steps. IC3 generally proceeds by alternating two phases, the blocking phase and the propagation phase. Now, I will explain the blocking phase, which is more important. In the blocking phase, we have a pair AI. Block AI means that IC3 will try to block marking A at frame Fi. In other words, IC3 will try to prove the upward closure of A is unreachable within S steps. These rectangles are frames which over-approximate coverable site. Now, given a pair AI, we try to prove the upward closure of marking A is unreachable within S steps. We write A upward below Fi and try to find a predecessor of A upward in Fi minus 1. In other words, we try to check if this intersection is empty. If not empty, then we extract a predecessor of A upward in Fi minus 1 and generate a new pair Bi minus 1. Now, we try to prove the upward closure of marking B is unreachable within I-1 steps. IC3 continues recursively until it finally generates a new pair, D0, which represents that SC3 has found a path from M0 to A upward, and we can see SC3 failed to block A at Fi. In other words, A is coverable within S steps. In the other case, if the intersection is empty, then the upward A is unreachable in S step from former frame. We write an empty set here to denote that A is uncoverable within S steps, and then we refine the over approximation of coverable site by removing A upward from Fi. Then I will briefly state the structure of SC3 for Petri nets. Input a Petri net and a target marking. SC3 initializes F0 with downward closure of the initial marking and adds a new frame F1, which is initialized with the set of all markings. SC3 generates a new pair MTK and tries to block MT at Fk. If fail to block MT at Fk, then a path from M0 to MT upward is found, and we can see MT is coverable in key steps. Then SC3 ends. Otherwise, if SC3 blocks MT successfully, then it extends the sequence and adds a new frame. And during this process, if two consecutive frames become equivalent, we can conclude that the set of all successors of Fi is a subset of Fi plus 1, and Fi is an inductive invariant, and we can say MT is uncoverable. Then SC3 ends. But if there are no consecutive frames become equivalent, then SC3 repeat this process, continue to generating a new pair MTK until SC3 ends. As we all know, SC3 is a very efficient technology for verification, but in this case, SC3 works on Petri nets with high dimensionality directly. And can SC3 perform better on Petri nets? Here is a method, we call it place merge abstraction. It can reduce dimensionality by merging some places of original Petri net into a single abstract place, and then get an abstract Petri net with lower dimensionality. Here is the definition of abstraction function. It is a surjective function and maps original place P to abstract place P hat. Here is an example. The figure showing left side is a Petri net. Then we merge red place into 1 and blue place into 1. Here is the abstraction function. It maps P0 and P1 to Q0 and maps P2, P3, and P4 to Q1. According to this function, we can get an abstract Petri net with only 2 places. After abstraction, we have this proposition. Given a Petri net N and their abstraction N hat, if target marking MT is coverable in N, then the abstract version of target marking MT hat is also coverable in N hat, but the converse doesn't hold. Then we have if MT hat is uncoverable in N hat, then MT is uncoverable in N. MT hat is coverable in N hat. We cannot conclude that MT is coverable in N, because there might exist spurious counterexample. Continue with this example. Distribution of tokens in 2 figures denote their initial markings. In abstract Petri net, there exists a path T0, T0 from the initial marking 03 to 21, but the same path T0, T0 is illegal in the original Petri net, because the second transition T0 is not enabled here. In this case, the path T0, T0 is an spurious path. We need to refine abstraction to rule out this spurious counterexample. Now, let's see when a counterexample is spurious. A counterexample pi is not spurious if and only if this formula is satisfiable in the original Petri net. In other words, the counterexample pi is legal in the original Petri net and can make the target marking MT coverable. Therefore, the path pi is spurious if either Ti is not enabled at Mi or each Ti is enabled at Mi, but the final relation does not hold. So there are two cases leading the counterexample spurious. After knowing when a counterexample is spurious, let's see how to refine an abstraction to rule out spurious counterexample. The first case, when Ti is not enabled at Mi, there must exist some places such that MIP is less than WPTI. These places lead to Ti not enabled, so we extract these places and merge them into a new abstract place. The second case, when each Ti is enabled at Mi, but the final relation does not hold. Similarly, there must exist some places such that MTP is greater than MKP. We also extract these places and merge them into a new abstract place. Continue with this example. After the first transition T0 fairing, there are no tokens to make the second transition T0 enabled. So, the place P2 is the K place. We extract it from abstract place Q1 and generate a new abstract place Q2. Therefore, according to the new abstraction function, we refine the abstraction and get a new one like this. Obviously, the path T0, T0 does not exist in the new abstraction. Finally, we try to improve the outperformance of SC3 by combining these two technologies, SC3 and place merge abstraction. We named it SC3 plus PMA. SC3 is the core verification tool of SC3 plus PMA, and place merge abstraction reduces the dimensionality of Petri net. SC3 plus PMA lets SC3 work on the abstraction with lower dimensionality. If necessary, the abstraction is refined. Here is the structure of SC3 plus PMA. First, it initially generates the closest abstraction by merging all places of original Petri net into one. Then, it checks abstraction by SC3. If uncoverable in abstraction, we can get an inductive invariant of abstraction, and then we can conclude that MT is uncoverable in the original model. Then SC3 plus PMA ends. Otherwise, if coverable in abstraction, we can get a counterexample pi, and then it's necessary to check whether the counterexample is spurious in the original model. If not spurious, MT is coverable in the original model, then SC3 plus PMA ends. But if spurious in the original model, we need to refine the current abstraction according to the spurious counterexample and get a new abstraction. Then continue to checking the abstraction by SC3 until SC3 plus PMA ends. The last part, experiments. We have collected almost 100 benchmarks from several sources and compared running time between SC3 and SC3 plus PMA. SC3 plus PMA outperforms SC3 on 53.75% of benchmarks, and dimensionality of abstraction allowing to conclude has decreased by 63.34% on average, comparing with the original Petri nets. This table shows benchmarks where SE3 plus PMA performs better. For example, at this line, Petri Net modeling conditionals has 214 places, but SE3 plus PMA can get conclusion on an abstraction with only 26 places and costs 1 second less than 5 seconds of SE3. But in this table, it shows benchmarks where SE3 plus PMA performs worse. I think there are two reasons. First, the efficiency of refinement method may be not so high. It may cause that SE3 plus PMA spends too much time on refinement. Second, after generating a new abstraction, we modify the data of a frame to adapt new abstraction. The way to deal with frames after refinement may be not so efficient. In the future, we plan to optimize the implementation to achieve better results and apply the approach to analyze more properties and models. Thank you for your attention.